For Pure Mathematics Paper 3, 2, February, March 2026. Question number 1. If you had solved this equation, 4 times 2, x plus 2, and minus 5 times 2, 2 minus x equals 3. So what we're going to do is that we're going to rewrite the equation in a nicer way, so that we'll be able to solve it. But then what we're going to do is to apply the one of the laws of indices, right? So if I have a exponent m plus n, this is the same as a exponent m times a exponent n. So that law says that whenever we are multiplying numbers with the same base, we just add the exponents. So it's a similar thing we see over here. There was an x plus 2, the power of 2, and then 2 minus x power of 2. So we're going to split them using this law of indices. So let's rewrite the equation. 4 here, and then times 2 exponent x times 2 squared, which is 4, minus 5 times, here again, 2 exponent 2 times 2 exponent negative x equals 3. Now let's try and rewrite them well. We have 4 here times the number here, 2 squared is also 4. So I'll write another 4 here before the 2x here, minus 5 times 4 times, and then 2 exponent negative x. We also apply this 2 exponents. Let me use a letter. A exponent negative m is the same as 1 over a exponent m. So the negative exponent doesn't mean the number is a negative number. It rather means that this number is a fraction. So 2 exponents negative x can be written as 1 over, or better still, you can write 2x negative 1, which simplifies to 1 over 2 exponent x equals 3 here. Now 4 and 4 will be 16 times 2x, and mind you, we can't multiply 16 and 2 here and get 32 exponent x, and the reason is simply because 2 has an exponent. Until we find what that value of x is, we can't solve this directly. We need to find the exponent here and then find out what the value of 2 exponent that exponent is before we multiply by 16. So this cannot be written as 32 exponent x, and that will be wrong. And then we continue, we have 20, then times 1 over 2x, which is an exponent, equals 3. So we have here 16 times 2x minus 20 over 2x is equal to 3. And over here too, we can't divide the 20 and 2 over here because 2 has an exponent which is yet to be found. So at this point, we see the x power of 2, the x power of 2, or 2 exponent x, 2 exponent x, which need to be solved, right? So what we're going to do is that we're going to replace 2 exponent x by any variable. So let's say y equals 2x. So we do substitution of this into this equation, and our equation becomes 16y minus 20 over y is equal to 3. And you multiply 3 by y to get a quadratic equation. 16y squared minus 3y and then minus 20 is equal to 0. So that becomes a quadratic equation, and then we need to solve this by any method of solving quadratic equation. I'm going to use a quadratic formula. So here we have y is equal to our a is equal to 16, our b is equal to negative 3, and c is equal to negative 20. So we do substitution into the quadratic formula: negative b plus or minus root of b squared minus 4ac all over 2a. So negative b, that makes positive 3 because b is already negative, plus or minus the square root of square root of b squared, and our b is negative 3, minus 4, a is 16, and then c is negative 20. So you can point this on a calculator and then get your answers all over 2 times 16. Then on my calculator, I found y is equal to 1.2162 3 decimal places or 4 significant figures, or y is equal to negative 1.0284 decimal 4 significant figures. Now we did the introduction of y, so we go back to our x. We already said that let y equals 2 exponent x. So each of these has to be replaced by, each of these y's has to be replaced by 2 exponent x. So I have 2 exponent x equal to 1.216, or 2 exponent x equal to negative 1.028. Then what do we do here? We take the length of both, so you can even take log to any base at all. What really matters is that if you take log to the base 10 at the left hand side, do the same thing to the right hand side, and your answers are going to be the same. So you take length of both sides, and you have length of 2x is equal to length of 1.216. Then we have x length 2 is equal to length of 1.216. Divide both sides by length 2, here by length 2, and then x is equal to approximately 0.282. Because the question says our answer should be left in 3 significant figures, this becomes our solution. However, at the other side, you take length of both sides, and then because of the right hand side, remember the domain of the function length is x is greater than 0. What that means is that length does not receive or does not accept negative numbers. So we don't have solutions at this part, right? The only solution we have is for this part, and this becomes our final answer. So question number 2. The complex number z satisfies the modulus of z equals 9, and the argument of z lies between half pi and pi inclusive. On the Argand diagram below here, sketch the locus of the point representing z. So you have to sketch all complex numbers on this Argand diagram that satisfy the two expressions given. One is an equation, the other is just a curve that we are supposed to sketch. You have to sketch so that both equations are satisfied. So first of all, let's start with the first one. Remember this expression or this equation. This complex number or this modulus of z minus z, let me use z naught, okay, is equal to r. This represents the circumference of a circle that is centered at z naught. So the center of the circle is z naught, where z naught is in a coordinate form. So z naught may be x naught and then y naught, and then radius is equal to r. So this equation represents on the Argand diagram represents a complex number whose represents the circumference of a complex number, or the circumference of a circle, right, centered at z naught and then with a radius of r. It means that from this we have z is equal to 9, can be written as z minus 0, 0, which is the center, equal to 9. It means that the equation given here, or the curve given here, is the circumference of a circle centered at the origin, or 0, 0, whose radius is 9, and we're going to draw that. If so, let me get back to this curve. If this less than were to equal sign were to be just less than or equal to, it means this would represent the both the circumference and the inside of a circle that is centered at x naught and y naught with a radius of r. If it's just less than, then it means we are only referring to the inside of the circle where the circumference is excluded. So the circumference should be drawn with breaking lines. And then if you see a greater than r, that means you are referring to the outside or the outer portion of a circle centered at z naught with a radius of r, and circumference of that circle is also not included in the curve. If it's greater than or equal to, means still the outer of the circle, but the circumference is included. So we go straight ahead and sketch the first part. So the first part is for modulus of z is equal to 9, which you've already described over here, that it's a circle centered whose center is 0, 0, and then radius is equal to 9. So I'm going to sketch that over here. So radius is 9, so we start from here, and then forgive my circle if it's not straight. If it's not, that's nice. Right? Let me use a different color for a reason that will be explained later. So we go from the other end, 9 here to the other 9. Then we move on to 9 again, then this. So this curve, modulus of z is equal to 9 is what we've drawn over here. A circle whose center is the origin O, and then with a radius of 9. But then because it is equal to, we only want the circumference and not the inner or outer part of the circle. Now next is, we're also looking for all complex numbers whose arguments are between half pi and then pi. On the Argand diagram, there are 4 quadrants. The first, we start measuring argument from the real axis. So for argument, what it means is the angle that a complex number makes with the real axis. For instance, if my complex number is here, let's say z1 is here, plotted over here. Then I draw a straight line from the origin to z1. The argument of z1 is the angle it makes with the real axis. That's theta over here, right? So from this question, we have to look for all complex numbers whose arguments are between half pi and then pi inclusive, right? And then on the Argand diagram, we can label them with angles. From the real axis, since that's where we start measuring the angle, 0 over here, or 0 degrees, and this is half pi or 90 degrees. This is 180 degrees or pi, and then down here we have 2 over 3 pi or 270 degrees. So if you are looking for all complex numbers whose arguments lie between pi and half pi, that means you're looking for all complex numbers in the second quadrant, because that's where you find those complex numbers between half pi and then pi. And because it is less than or equal to, it means that the axes are included. So we are looking for all complex numbers over here in this second quadrant, everything shaded, right? I'm going to do the final work later, so let me just say this part. So all complex numbers over here is what this curve is talking about. However, because you are to draw the locus of points that satisfy both curves, we must indicate where the two shadings meet. First of all, the first curve is just the circumference, and the second curve is everywhere in the second quadrant. So where the two curves meet is just the blue line, right? What we're going to do is that we're going to delete every part of the curve and leave just the blue line, because that's where the two curves meet, right? And let me explain further. The reason why we're going to erase every other part is that, let's say I pick a complex number somewhere here, right? Let's say z1, right? Even though z1 has 8 arguments, so the argument is right from this line starting from the real axis. So these arguments will lie between half pi and pi, or 90 and 180 degree, because in the second quadrant. But then we expect this complex number for it to be part of the curve. It must also satisfy the first equation, or the first curve, which says that the this point must lie on the circumference of the circle centered at the origin, and then with a radius of 9. So all points below the blue line will not satisfy the first curve, and all points outside the blue line or above the blue line will also not satisfy the first curve, but will only satisfy the second curve. Therefore, the only answer, or the answer we're looking out for, will be just the blue line. So every other thing will be erased except the blue line, and that becomes our curve. So that's it. So our curve is just the an arc, right? An arc in the second quadrant. Now B says that on the same diagram, sketch the locus of the point representing z star plus 3. Remember, z star means the conjugate of z. But before that, let's do some short exercise here. Let's just write one complex number that can be plotted here. Let's say my z is equal to 3 plus 3i. Right, so 3 plus 3i is here. This is z. Right? And then z star is a conjugate. That's going to be, just change the plus sign to those six, which is negative minus 3i. When you plot this, it's going to be here 3 minus 3i, and this is z star. So you check these two things carefully, and then you realize that the conjugate of a complex number on that diagram is just the reflection of that complex number in the real axis. Right? So this star just means that we are just to reflect a complex number with the real axis as the mirror line. So you realize that the z star here is just the reflection of z over here. Now again, let's add a number. I'm trying to add z star plus, let's say, 2, which means that we're going to add 2 to the z star over here, giving us 5 minus 3i. And let's try plotting 5 minus 3i. 5 minus 3i. 5 is somewhere here. Let's assume it's here. And then minus 3i also here. So this is z star plus 2. And you see that it is also just a shift, right? Because the number we added is a real number, it's going to be a shift. So if I have z and then I add 3, and I want to plot this on another Argand diagram, what I'm going to get is that it is just a shift of the, or translation of z 3 units to the right, or by positive 3 units on a real axis. So that's basically the information we need to solve the B parts. Yeah, so this, we just need to do this z star plus 3. Now we understand z star just means a reflection in the real axis, and plus 3 means a translation or a shift by 3 units on the real axis. Because it is positive, we're going to go right on the real axis. So let's start with z star. Z star means we should just reflect the diagram that we drew first. So this blue line or blue arc is going to be reflected in the real axis, or in the x-axis, if so to say. So let's do that. Reflecting the 9i here in the real axis means you're going to have negative 9i. So that's going to be the reflection, right? And then we also need to reflect negative 9 on the real axis, using the real axis as a mirror line. That's one will still be at the same point. So just the z star alone, I will do the plus 3 later. So z star alone means that we need to draw an arc over here, just as you've drawn on the blue line. But I'm using broken lines because that's not our final work. Now next is z star plus 3, right? The conjugate plus 3. And we've already understood that plus 3 just means that we have to shift this 3 into the right because it is plus 3. So let's do that. Let's shift them by shifting the point here. So for the negative 9 over here, if you have to shift it 3 units to the right, that means you're going to get to negative 6 over here. And then for the negative 9i here, we shift it 3 units to the right. It means it has to be directly below the positive 3 on the real axis. Now this is our final work. So we now draw the arc right from the negative 6 on the real axis to 3 negative 9i here, and that's our final work. The broken lines are to be erased since they are not parts of the work. That was just the process leading to the final thing, and this is exactly what we expected to do. Now question number 3, find the exact value of this integral 3 sine x sine 2x from 1 a quarter pi to 1/3 pi. And our answer must be given in set form where p and q are rational. So first of all, we see a sine 2x here, and that's what we need to deal with. We need to rewrite the sine 2x into one that will be easier for us to solve. So remember, we know that, and we're expected to know that sine 2x is equal to 2 sine x and then cos x, right? So this is an expression for sine 2x, which we expected to know. So we go back to the question and replace the sine 2x by 2 sine x cos x. We're going to rewrite the question. So the question now becomes the integral of, so here 1/3 pi to 1/4 pi, and then I write a 3 outside since it's a constant. And sine x here, then a sine 2x will be replaced by another sine x, and then cos x, and our dx also comes as well. That means we are trying to, sorry, there was a 2 here that is supposed to be included. It means we are trying to integrate this. The 2 goes outside and multiply the 3, giving us 6. Then 1/3 pi over, and then 1/4 pi as well. Then here we have sine squared of x and then cos x. Then begin to think about it. There are different methods that we use in integration. So when it comes to functions of this nature, whether they use substitution or work, or sometimes if the functions are two different functions, for most of the times, it means you're supposed to use by parts. I look at this and then, so what gives you a hint that the use substitution will work is if mostly if the differential of one gives the other, right? If the differential of one of these functions gives the other, you realize that when we differentiate sine, we get cos, and sine is the one that has a square. So I'm going to use u substitution and let u equal to sine x. So when we are replacing a function in the integral by u, you don't need to include the square. So for instance, what I'm saying is that we let u equal sine x only. Don't use sine squared x, right? And then if we had the roots, right, we would have let u represent the whatever expression is under the root sign and not the root sign included or inclusive. So we have our u equal to this. That means that since we are trying to introduce a u, means we're going to do a change of variable, right? Every variable that is x here has to be changed to u because we're trying to change sine x to u. So everything x here must be changed to u. That means our dx here must also be changed to u, as well as our limits. The limits here, 1/4 pi and then 1/3 pi are defined for x. But then if you are trying to change the variable to u, then we need to redefine our limits try to find what would be the value of u or values of u given these values of x. That's 1/4 pi and then 1/3 pi. That's one way. The other way is that you can also decide to keep your limit there, right? When you finish the integral, then you bring back your x, your sine x, so that you don't need to necessarily change the limits. So that's the approach I'm going to. I'm not going to change the limits. When I finish everything, I'll bring back sine x so that the limit will be kept in our calculation. Now let's continue from here. If u is equal to sine x, then let's differentiate it. Du dx is equal to cos x, which means that du is equal to cos x dx. I'm going to rewrite the question. Okay, let's make the dx the subject. We divide both sides by cos x so that dx will be equal to du times 1 over cos x, or du over cos x. So I'm going to rewrite the question, and then I would do all the substitution, the necessary substitutions, and make sure that all the x's in the question go away. As I'm going to rewrite the question here, so we are trying to integrate 6, an integral of from 1/4 pi to 1/3 pi of sine x squared. Remember, sine x has been replaced by u, so sine squared x means I'm going to have u squared. I'm going to write my cos x like that because I know they're going to cancel out. Then now dx is now being replaced by du over cos x. So times du over cos x, so that this cos x and this cos x will be dealt with. Now we have 6 integral of 1/3 pi over and then 1/4 pi, sorry. Then I have u squared du. Now you realize that everything except the limits are defined for u, right? So that we can comfortably do our integration. So the integral of u squared is going to be u cubed all over 3, the new exponent, and 6 out. And you bring a limit 1/3 pi and then 1/4 pi. I can write 6, so I can bring the 3 out so that it becomes 6 over 3, making 2. Then I have over here 1/3 pi and then 1/4 pi. Right? So instead of writing the u cube, now what I have in the bracket is supposed to be u cube. Because I did not change the limits, right? I kept the initial limit that were given in the question. I'm going to replace the u by what it is. I know I replace sine x by u, so I'm going to replace sine x here. And because it is u cube, it's going to be sine cube x, right? If I change the limits so that the limits were redefined for u, then there wouldn't be any need for me to bring the sine x over here again, since the limit has been changed. But then that wasn't what I did, so I need to bring the sine x back. Now the next thing is to do a substitution, right? Substitute the upper limit first before the lower limit, and then you subtract them. So I have 2 out here, then we substitute the 1/3 pi, so I'm going to have sine of 1/3 pi, or pi over 3, all cube. Remember, sine cube x is the same as sine x all cube. So minus sine of 1 over 4 pi, or pi over 4, and then all cube. That is all. And our 2 is outside to multiply after our final answer in the brackets. So in the calculator, I have this 2 outside here, and then I have for the sine pi over 3, That's same as sine 60, and that is root 3 on 2. So I have root 3 over 2 all cube minus sine 1/4 pi, which is the same as sine 45. So that's root 2 over 2 exponent 3. And let's try and simplify. That gives us 2 outside. Then I have root 3 over 2 all cube is going to be 3 root 3 over 8. And then minus 2 no, root 2 over 2 exponent 3 has to be root 2 again over 4. Right, root 2 over 4, because 2 will cancel the 2 that will come up there. And that's it. So finally we have our answer to be 3 over 4 root 3, then minus half root 2. That's what the question asks us to do. It asks us to leave our answer in set form, and that's exactly what. So P and Q are the numbers multiplying the set. So P is 3 over 4, and then Q is negative 1 over 2, and that's our answer. So question number 4, the coefficient of x cubed in the expansion of this binomial is 1, and then we have to find the value of a. So this is a binomial expansion, and you check the formula page and you see it's over here. So mostly for when the first term or the binomial to be expanded has a 1 in it, like this one, it has a 1 starting. So we apply this formula, right? So we are looking for the coefficient of the x cubed term, and that is this term. So we just need to quote this one where n is rational, and then do a substitution and find the coefficients, after which we are going to equate to 1, since the question says the coefficient is 1. So from here, our n is the exponents, just as we find in the formula. And so n is equal to 2 over 5, which is the same as 0.4, right? And then the 1 is already there in the expansion. After the 1, whatever is left is our x. So we compare that to this and realize that our x is equal to negative ax, right? So this we're going to do, this the substitution we're going to do. Of course, we can replace the x by negative a instead of the x because we just need a coefficient. But anyways, we can still include it, and then when we are done, we discard it. So now we know the x cubed term can be found this way. The coefficient can be found using this formula. So I'm going to quote this formula and then do substitution. So the coefficient of x cubed is given by n minus 1, n minus 2, then divided by 3 factorial times x squared. The x squared will give us the x term. We can do that by replacing, instead of x cubed, we replace by negative a, or we can still write an negative ax. So I'm going to do x cubed, and when we get here, I'm going to replace the x cubed term by negative ax. So that gives us 0.4. I'm using a decimal. Then 0.4 minus 1, again 0.4 minus 2, all divided by 3 factorial, which is 6, and then times x cubed. These are x, negative ax exponent 3. I'm going to point this on the calculator and find my value. So we have negative 8 over 125 a cube, and then x cube, but then I just need the coefficient, and so that's all. So this is a coefficient of x cube, but the question says that that coefficient is equal to 1. So we need to equate this number to 1 and then we solve for a. Alright, so you multiply through by negative 125 over 8 here by 125 over 8 negative, and then this part cancels out and we have a cube is equal to negative 125 over 8. We take the cube root of both sides, and then we have the cube root of negative 125 is negative 5, cube root of 8 is positive 2. So our a is equal to negative 5 over 2, or you can write negative 2.5, and that's the value for a. Question number 4b says, hence find the coefficient of x4 in the expansion of this expression 2x plus 1 and then 1 minus ax to exponent 2 over 5. And so we need to find the coefficient of x4. And since these are two binomials that are multiplying, let's do something here. 2x plus 1 has no other expansion because it doesn't bear any other exponent apart from 1. But then the second term, second binomial, 1 minus ax exponent 2 over 5 has an expansion. So you need to find out which terms are we going to multiply with the first binomial to produce the x4 term in our expansion. So let me write 2x plus 1 here. And let's assume the expansion of the second one, the second binomial is 1 and then something x and then something else x squared, something else s cubed, something else s4, right? We need to find out what do we need to multiply to produce x4. So you realize that we need the coefficient of, we need the x4 term in a second expansion to multiply 1 over here. And then to get another x4, we also need the x cubed term to multiply the 2x over here. That means that the coefficient of x4 in this expansion has to do with the coefficient of s cubed in the second binomial times 2 over here, and then the coefficient of x4 in the second expansion times 1, and we add both the results after everything, then we get the coefficient of x exponent 4. So let's start by finding the coefficient of x exponent 4 in the second expansion before they look at the formula. So we use the formula to find the coefficient of x cube. We're going to do this similar thing to find the coefficient of x4 in this case as well. So the coefficient of x4 will now be given by n, then n minus 1, n minus 2, n minus 3, all divided by 4 factorial, and then times ax, or times x exponent 4 in this case. And we've already found our a to be negative 5 over 2 or negative 2.5, so I'm going to do a substitution. Our n already is 0.4, so I'm going to do a substitution and find the coefficient of x exponent 4. So 0.4 here, 0.4 minus 1, 0.4 minus 2, 0.4 minus 3, divided by 4 factorial. That's going to 6 times 4, which is 24. And then times negative ax squared. I need not to include the x because the x will give us the x4 term. I just need the only the negative a. Our a is negative 5 over 2. So negative 5 over 2 exponent 4. And this on the calculator gives me negative 13 over 8. So yeah, remember this is multiplying. Negative 13 over 8. So this is the coefficient of x, the x4 term. Can add it to it. So this is the x4 term in the expansion of this. And you've already found the coefficient of the x cubed term from the previous section. So now the coefficient of x4 in the expansion of this of x exponent 4 will now be equal to, as we said earlier, 2 times the coefficient of x cubed in the expansion of this, which has been done previously. Realize the coefficient of that is over here. We had negative 8 over 25 a cubed. A has already been found. I'm going to do that over here. Negative 8 over 125, and then a cubed plus 1 times the coefficient of x4 is negative 13 over 8. So let's simplify this. We have a negative 16 over 125 times negative 5 over 2 for a cubed, and then minus 13 over 8. That gives us 2 minus 13 over 8. And now we have 16 minus 13 is 3 over 8. So this is the coefficient of x4 in the expansion of the binomial given over here, and that's our solution. 4c states the set of values of x for which the expansion in 4b is valid. So the set of values of x for which this expansion given over here is valid, right? So you realize there's nothing wrong over here. I mean, there's no kind of suspicion in the first binomial because it doesn't need any special expansion. But the second binomial does, right? At what point will this binomial fail to expand? So you go back to the formula sheet and then you find it here. It says that this expansion is valid only when the modulus of x, right, or the absolute of x is less than 1. What that means is that only when the second term here, its absolute is less than 1. We're going to do similar thing for this question. So you're going to say that this expansion will only be valid only when the second term, negative ax in modulus, is less than 1. And that's exactly what we're going to do. So expansion is valid only when negative ax is less than 1, right? So these are the set of values of x for which the expansion in 4b is valid. But we've already found our a, so we just need to do substitution. Our a, we found it to be negative 5 over 2. We have negative 5 over 2 x is less than 1. And as a rule, we can factor out the 5 over 2. Or better still, it becomes 5 over 2 negative here, and then x less than 1. And because it is a modulus, 5 over 2 becomes positive. In other words, you have 5 over 2 modulus of x is less than 1. We solve this and then you multiply through by 2 over 5. And you have the modulus of x is less than 2 over 5. So this expansion in 4b is only valid when the modulus of x, whatever value of x that we place over there, its absolute value must be less than 2 over 5. Other than that, the expansion will not work. Question number 5. It is given that the complex number is equal to this, where lambda is a real constant. Find the value of lambda for which the argument of z is equal to 1/4 pi. So the argument of z, so let me draw an Argand diagram, do a sketch of Argand diagram here. Over here. And this is the real axis. Right? So the argument is measured from the positive real axis. So for this particular constant number, where lambda is a constant to be found, it lies somewhere here, and its argument is 1/4 pi, which is the same as 45 degrees. And to be at the 45 degrees line, then your imaginary part and the real part must be the same, because the Cartesian equation of this line is y is equal to x, and that's the 45 degrees line. So that means that this complex number has its imaginary parts to be equal to the real parts. Other than that, its argument cannot be 1/4 pi. So that's one information we need to, as we proceed in solving this. We know that the imaginary of this complex number is equal to the real parts of this complex. That's one way that we can solve it. There are different other methods, but this is going to be easier for us. But before that, for us to determine the imaginary part of this and in the real part, we need to write the complex number in a Cartesian form, like x plus iy, where y is the imaginary part and x is the real part. So we're going to rationalize or conjugate this complex number by multiplying both numerator and denominator by the conjugate of the denominator. Then we write it in a simpler way. So you have z is equal to 3 plus lambda I over lambda plus 2i multiplied by the conjugate of the denominator, which is lambda minus 2i over lambda minus 2i. Then we multiply numerator by numerator, denominator by denominator. So let's see. Multiply both numerators. So 3 times lambda will give us 3 lambda. And then we will have okay, let me do step by step. We have 3 lambda, and then 3 times this will give us negative 6i. Then lambda I times lambda will give us plus lambda squared I. Then lambda I times negative 2i is going to give us, first of all, negative 2 lambda I squared. But I squared is negative 1, which will end up making this one positive 2 lambda. So this is going to be positive 2 lambda because of the I squared. All divided by, remember, when you multiply a complex number by its conjugate, the result is always the real part squared plus the imaginary part also squared without the I. So the imaginary number is 2 squared. And let's simplify the numerator, and then we get our solutions going. So it means that our z is equal to 3 lambda plus 2 lambda. That gives us 5 lambda. And then we also have the imaginary parts. We can group them here by factoring out the I, so that we have plus lambda squared minus 6 all times I divided by the denominator. However, we can write it this way. I can write the denominator this way, lambda squared plus 4, and then here also lambda squared plus 4. That means that the real part of z is the first term, the one without the I, that is 5 lambda over lambda squared plus 4, and the imaginary part of z is lambda squared minus 6 divided by lambda squared plus 4. Before we establish that, since we are looking for the value of lambda for which the argument is 1/4 pi or 45 degrees, it means the imaginary part should be equal to the real part. So over here we just equate the imaginary and then the real part. If you like, you can just use a tan inverse formula thing to do, and then you're still going to get the same thing. So the imaginary of z must be equal to the real of z for the argument of z to be 1/4 pi. So we have 5 lambda for the real parts over lambda squared plus 4 must be equal to lambda squared minus 6 all divided by lambda squared plus 4. The denominators are the same, so we equate the numerators, or better to multiply through by lambda squared plus 4. So we have 5 lambda is equal to lambda squared minus 6. Now it becomes a quadratic, and then we need to solve this. We arrange everything to one side and solve it as we solve normal quadratic equations. So we have lambda squared minus 5 lambda minus 6 is equal to 0. Right. Solve this and we have so lambda here minus 6 and then minus plus 1 to get negative 5 equal to 0. So you have two values of for lambda. Lambda is equal to 6 or lambda is equal to negative 1. But you go back to the question and check something. It says that find the value of lambda. So it means that we just need one value for lambda, not values. But we found two values. Now what we do is that we substitute these values of lambda into the complex number. Remember, because the argument of lambda is argument of z is 1/4 by 45 degrees, it means it is in the first quadrant, right? Z must be in the first quadrant over here and not any other place. Now let's go back to, it means to be in the first quadrant, the row parts must be positive and then the imaginary part must also be positive. Now if you substitute the 6 into the row parts of the complex number, right? The row part is 5 lambda over lambda squared plus 4. Lambda squared plus 4 will always be positive because of the squared. And then 5 times 6 will also be positive 30, right? So yeah, 6 will make the row part positive. Now do the same thing, substitute lambda equal to 6 into the imaginary part, which is over here. So we have 36 minus 6, that's going to be 30 over 36 plus 4 over 4, that's for 3 over 4 I. So when lambda is equal to 6, z lies entirely in the first quadrant. So yeah, 6 is a solution. However, when we pick lambda is equal to negative 1, you substitute into the row part and you have negative 5 over 1 plus 4, giving us negative 1. Right? Negative 1 on the row part means we are going somewhere in the second quadrant or the third quadrant, which cannot be the case for a complex number whose argument is 45 degrees or 1/4 pi. Therefore, we can conclude that lambda is equal to 6 and not negative 1, because only 6 gives us z in the first quadrant. Now 5b says when lambda has a value found, that is when lambda is equal to 6 as we found in 5a, find the exact value of the modulus of z, making your method clear. Right? So you know the modulus of a complex number, if z is equal to x plus iy, then its modulus is given by x squared plus y squared or another root sign. So we need to substitute this 6 into the real part and then the imaginary part. But then we already established that the real part and imaginary parts are equal. So substituting this 6 into the real part only or the imaginary part only is enough for us to get the value of x and y over here. So our z is equal to the real part of z, first of all, is equal to, we already said that is 5 lambda over lambda squared plus 4. So that's going to be 5 times 6 over 6 squared plus 4. And that is going to be 30 over 40. So you have 3 over 4. That's the real part, which is also the same as the imaginary part of z. That means our complex number is 3 over 4 plus 3 over 4i. Now it's easier now to find the modulus. That means that the modulus of z is equal to 3 over 4 all squared plus 3 over 4. Of course, you can write 2 times 3 over 4 all squared with the 2 outside. So yeah. Then we have equal to 9 over 16 plus 9 over 16. That's supposed to be 18 over 16 right here. And then root of 18 is 3 root 2. Root of 16 is 4. So that is the modulus of z. Now question 6. The polynomial given here is denoted by p of x, and it is given that x squared plus x plus 1 is a factor of the polynomial here. You have to find the values of a and b. Yeah. So since the factor given is a quadratic, okay, and then the polynomial is a quartic one or has a degree of 4, it means that the other factor that we need to multiply by this factor to get the polynomial is also a quadratic. That's the only point you're going to get an x4 or x exponent 4. So what that means is that 2x4 plus ax cubed plus 4x squared plus bx minus 3, which is a polynomial, is equal to or equivalent to the factor given x squared plus x plus 1 times another quadratic, because that is the only point you are going to produce this particular polynomial. So that quadratic could be px squared. Let me use a different variable here. Could be mx squared plus px plus, let's say, a c. Right? So we need to expand the right hand side and we expect to produce the left hand side. However, we can do some source analysis here to find some of the values, and then we continue from there. We want to find out how are we going to produce the 2x4 or 2x exponent 4 from this expansion. That will happen only when we multiply the first terms from each quadratic. So this term times this term will give us the x4, right? But the number here is 1. 50% of this in this part is m. So we just need to find out what number should m be, so that when we multiply by 1, we produce a 2 here. Probably or certainly m has to be 2. So I'm going to erase m and replace it by 2. Then we can also do the same thing for a similar thing for the constant, right? The constant term here is negative 3. And how are we going to produce that negative 3 from these two expansions? It has to be the one here multiplying c. Since this is 1, we look for what number should c be, so that when we multiply by 1, we get the negative 3. That means c should certainly be negative 3. So I'm going to erase the positive c and replace by negative 3. So by this, we've been able to find um, the values for c and then m. Right now, we can do a short analysis and find the values for b and then a. Right? Okay. So one way is that we can decide to expand the right hand side fully, and when we finish, we compare with the left hand side, compare coefficients, and then we get the values for a and b. Another way we can also go about this is to do it this way, to find out what values are we going to multiply to produce uh, b over here from this expansion, right? What value do we need to multiply to produce 4 over here from this expansion? And then we get our answer. So let's try one of them. So we ask, how are we going to produce px over here, or produce x, the x term, from these two expansions? So we're going to produce x by multiplying this by this. So x times 2 will be 3x. And then also multiplying 1 by this px. So those are the only two possible ways to produce an x. That means that the bx from the left hand side must be equal to negative 3x. So I'm just multiplying the one the arrows are pointing. And then 1 times this will give us plus px. That gives us b is equal to negative 3 plus p for a first equation. Now next is I just want the term that will give me the b and then the a, right? So that I'll have equations that have a, b, and then p in them. So next we are looking for what terms need to be multiplied to produce a x cubed term, so that we put that those terms to a. So let's start from the expansion on the right hand side. So what terms need to be multiplied to give us x cubed? We need the x squared term here to multiply the sorry we need the x squared term to multiply the x term over here. I think there was a square written over here. Yeah. That's so the x squared term times the px will give us an x cube. Then we also need the x term here to also multiply the 2x squared here, and we get an x cube. Those are the only two possibilities to produce an x cube term. That means that ax cube at the left hand side should be equal to 1x squared times px. That's going to be px cubed. And then 1x times 2x squared is going to be 2x cubed. That gives us another equation. Dividing through by x cubed will give us a is equal to p plus 2 as another equation. Then finally, we need to find which terms need to multiply to give us x squared. Right? The reason why we need to find another equation is because we have um, three variables to solve. Right? We have p, b, and an a to solve, but we have just two equations. It means that we need an extra equation to solve it. So we're going to find out another equation. And as I said, this is the same as expanding the right hand side and then equating the coefficients. So let's find out which terms will give us the x squared. You know, x squared over here is 4, right? So let's find out which terms will give us the x squared from the right hand side. I need to multiply the constant here by 2x squared to get an x squared term. I also need to multiply the x term here by px to get um, an x squared term, and then lastly x squared here by the constant here to get an x squared term. So I'm going to do that and equate everything to 4x squared at the left hand side. So we have 4x squared at the left hand side is equal to, so here's 1 times 2x squared, that's going to be 2x squared, and then x times px is going to be px squared, and lastly 1 times negative 3 and then x squared is going to be minus 3x squared. Now dividing through by x squared, we have 4 is equal to 2 plus p and then minus 3. Right. This will make it easier for us to solve for p over here in the last equation. So we have 4 is equal to negative 1 plus p. Then our p is equal to 5. So that gives us the value of p. Now we can substitute the value of p into these two equations, and then we find the value of b and p. B and a, right? So it means that our a is equal to 5 plus 2. A is equal to 7, right? Then the value of p is 2 over here, so we do that into the equation for b, and then we find the value of uh, b. B is equal to negative 3 plus 5. Now b is equal to positive 2. So yeah, and I said once again, this is the same as expanding the right hand side and then equating the coefficients to find the values of a and then b. So a is equal to 7 and b is equal to 2 are our answers. That means our p of x can be written fully as this: 2x exponent 4 plus a is 7, 7x cubed plus 4x squared plus bx, which is 2x, and then minus 3 as our p of x. Right, question 6b says that hence show that x plus 3 is a factor of p of x. Remember, hence means that we are to continue from the previous session. Otherwise means that we can start all afresh. And it says hence, so it means that we are to continue from here. To show that x plus 3 is a factor of p of x, then x plus 3 is equal to 0 implies that x is equal to negative 3. We are to show that p of negative 3 is equal to 0. If that is true, then it means that x plus 3 is a factor. So we just need to substitute x equal to 3 into the p of x that we had over here. So p of negative 3 is equal to 2. Negative 3 exponent 4 is 81 plus 7 times negative 27, or negative 3 times 3 plus 4 times negative 3 squared, which is 9, plus 2 times negative 3 and minus 3. So let's try simplifying these ones. The first one we have 1, so this is equal to 162. Here we have 27 times 7, 189, and then 9 times 4 is 36, positive 36. Then we have negative 6 minus 3. Then you solve all these things and then you have everything is equal to 0. So therefore x plus 3 is a factor of p of x, since p of negative 3 is equal to 0. That's our solution. Y, and on the right hand side we have x over e3x dx. Right? I think I can rewrite the right hand side and write it this way. So I have here y over y plus 5 dy is equal to x e negative 3x dx. Right, so that's the first step. The first step is to separate the variables, and by that we mean let the x term go to one side and the y term to the other side. And number 2 is to integrate respectively. So by respectively, I mean that we integrate the left hand side with respect to y, and then the right hand side with respect to x over here. So these are two different functions, and then they require different methods of integration. Right? So let's attempt the left hand side. How are we going to integrate the left hand side? So let me write for the left hand side here. For the left hand side, there are two ways you can integrate this, right? At least two ways. Because this is an improper fraction, right? Rational fraction or rational function. It's improper because the degree of the numerator is the same as the degree of the denominator, which is 1. You can decide to do a long division. Right? Long division, write your y plus 5 here, and then y inside. So 1 here, y plus 5, and then you have negative 5 as a remainder. It means that we can write y over y plus 5 as 1 minus 5 over y plus 5. That's one way, and then we do our integration. So I'm going to write that over here. You may want to show this on your paper. That's also fine. Right? So this is the same as 1 minus 5 over y plus 5, and then dx, integrating everything over here. Right? This is going to give us the first one is going to give us, so integrating in terms of y, not x, y here. The first one is going to give us y, then next is going to give us minus 5 ln of y plus 5. Right? You don't need to add any c to it. You may want to do it over here, but later on when we are done with everything, after the x factor, so we're going to add our constant of integration. So that's just one way of integrating the left hand. So left hand side has been integrated over here, right? I'll call this star, or left hand side anyways. And another way we could have also done this is to use a u substitution by letting u equals y plus 5. That's the denominator, right? That means that y is equal to u minus 5. Then do a substitution of this into the function. You're going to get y at the numerator, that's going to be u minus 5, and then over u. So you're going to have 1 minus 5 over u, which is, then you integrate this and get u minus 5 ln u. Meanwhile, u is equal to y plus 5. Do your substitutions and then you realize you're going to get the same as we found over here. So that's just by the way, one of the ways that you can also do that integration. Okay, next we tackle the right hand side, which has to do with x. So the right hand side has this function. Let me use a different color for that. So this function, and how do you also go about this? We have an x here, we have an exponential here, right? So it means there are two different functions being multiplied over here, or we are trying to integrate products of two different functions, right? So that is one of the reasons that we need to know that we need to use by parts, integration by parts, right? So there are two functions. One is, this is how you go about it. There are two functions, and one of those two functions may be one of these LIATE, right? This is a logarithmic function. This is a an inverse trig function. This is an algebraic function, which is x squared, any polynomial function. This is a trigonometric function, and this is an exponential function. What if any of this is found in the integral, right? That one has to be replaced by u, right? So remember, for integration by parts, this is a formula from the formula book or sheet. So this is u dv dx. In fact, if I cancel this and this out, right, I have integral of u dv is equal to uv minus integral of v du, right? So what we are doing here is, which one do you represent by u? We know we have two functions that are multiplying and we need to integrate them. Which one do you represent by u? And so, and this is what I just wrote over here. U is equal to either the logarithmic function in it. You don't have logarithmic function, so you move on. Inverse trig. I is inverse trigonometric function. There's no inverse trigonometric function here, so we move on. The next one is algebra, which is any polynomial function. Alright, so because x is a polynomial function, that becomes our u. If there were no polynomial function, we would have now moved on to trig function. And if there is now, move on to exponential function. But because there was an algebraic function, which is x, right, that is going to be our u. So for the right hand side, for the integral of x e minus 3x dx, we let our u be equal to x, and then remember the formula is integral of u dv is equal to uv minus integral of v du, right? So u is this, and then whatever is left after picking your u becomes your dv, right? Because we are trying to rewrite the function as u dv. So after picking out the x, what is left is the whole of this, so that becomes your dv. So dv is equal to a negative 3x and then dx. And in the formula, we need to find v. We also need to find du. So we find them from here. Du dx is equal to 1. So du is equal to dx, or 1 dx. Then, since this is dv, it means there is a v function that has been differentiated. So we integrate that to find our v. So integrating this, you find v to be equal to the integral of this is, you repeat the same thing, e or exponential of negative 3x, and then divide by the differential of the exponents. Differential of negative 3x is negative 3. So divide by negative 3 over here. So that's our v. Next, we go back to our formula and do substitution. So the integral of x a negative 3x dx is equal to, it says u times v. Our u is x, so x, and our v is the whole of this, so exponential of negative 3x over 3, but it's negative over here. Then minus integral of v du, integral of v, our v still remains this exponential of negative 3x over 3, that's negative, so negative affect this part, making it positive, and the over 3 can be written outside, so that it becomes 1 over 3, and then I'm going to erase the over 3 since it has been written outside. It's a constant. Now we move on. Then the next is du. Du has been found to be 1 dx or dx, so it comes over here. So keep on integrating. Since we still have an integral sign here, we need to find this as well. So the integral still remains negative xa minus 3x all over 3, and then we integrate this, right? We've done that over here already, so we can just write that over there. So minus 1 over 3 here, and then e negative 3x divided by negative 3, right? That makes this part, the 3 here, 9. So I'm going to erase that and replace it by 9. And I hope you know why the plus sign has changed to negative, because we're going to divide by negative 3. So you have 1 over 9 over here. Then maybe we can add our c, right? So we are done with the right hand side. We had this. We are done with the left hand side. We had this, right? So we're just going to write them side by side, right? The left hand side goes to the left, right hand side to each position, and then we are done with our integral. So on the left hand side we have y minus 5 ln of y plus 5. Then at the right hand side, just as we've had, was negative 1 over 3, then x exponential of negative 3x, then minus 1 over 9 exponential of negative 3x, then plus c. Remember, the question gave us an information that when x is 0, y is 0, and the reason why that was given was to help us find the value of the c over here. So before I do the substitution, if you use the other method where I said that you need to use u substitution, you're going to get the left hand side to be y plus 5 minus 5 ln of y plus 5. So there's going to be a difference of 5 here, and there's absolutely nothing wrong with that. Okay, this 5 is a constant, and it doesn't appear in this one because it will be captured in this constant, right? 5 is a constant and c is a constant. So if you have this one, your value for c will be different from my value of c, because this one, my own captures this 5 inside the value of c over here. So there's nothing wrong if there is a difference of a constant in our integral, right? So let's move on. So when x is 0, y is also 0. So we put x0, y0 into this equation. So we go, this is going to be 0 minus 5 ln of 5, because it's going to be y plus 0 plus 5, then equal to negative 1 over 3. So everything goes 0 because this side goes 0, right? X becomes 0, so everything goes 0. Then minus 1 over 9 e exponent 0, and then plus c. Right? So the 0 is out over here, everything here also goes 0, and this is 1. So it means our c is equal to, I'm going to send this to the other side of the equal sign. So we're going to have 1 over 9, then minus 5 ln of 5. And that should be our value for C. If you had used this one, you would have had C is equal to 46 over 9, then minus 5 ln 5. And as I said, this 46 over 9 is the same as 1 over 9 plus 5, right? So 1 over 9 plus 5 gives us 46. It shows that even if you had this as your integral, this 5 will be captured in the value of C, and then nothing really changes over here. So now we can rewrite our entire equation again. Going to write y minus 5 ln y plus 5 is equal to we have negative 1 over 3 x e negative 3x minus 1 over 9 exponential of negative 3x, and then plus c. Now we know c is 1 over 9 minus 5 ln 5, right? At this point, you can decide to rearrange them, group the ln terms nicely, and then write them as one expression, or try to write your equation nicely. That's fine. The question says find an expression um, in terms of x and y, right? So this is enough. This suffices as your answer. However, if you want to write them nicely or factor out some 1 over 3 or 1 over 9 or something to just make it look nice, that's also fine. But other than that, I will leave this as my final answer for the integral. Question number 9. Let I be given as this integral using the substitution x equals to 3 tan u, so that I can also be written in this form, right? So just using the substitution and showing that I can be rewritten or can be written in this form. Um, yeah. So we have an expression for x, right? And we have an x cube here. What that means is that we just need to find the x cube over here. We can work on the integrand. Do a substitution, find what x cube will be given this substitution, find what 3 plus x squared will be, and then do the division. When we finish with our final, and then we bring everything back to the integral sign. So that's exactly what I'm going to do. But I will start with the limits, right? Since x has been replaced by 3 times u, then you find what happens. Remember, this limit I defined for x. And now that we are trying to change everything to u, we need to redefine the limit for u. So when x is 1, what happens to u? And when x is 3, what happens to u? So when x is 1, it implies that 1 is equal to root 3 times u, right? Divide both sides by root 3 and take the tan inverse of both sides. It means that u is equal to tan inverse of 1 over root 3. That is tan inverse of 1 over root 3, and that is pi over 6, right? 30 degrees. Same applies to the other side. When x is equal to 3, u is going to be tan inverse of 3 over root 3, which is the same as root 3, I think. And that's going to be pi over 360 degrees, right? So when we get back to our integral, we're going to replace the 1 here by pi over 6, and then replace the 3 by pi over 3. And that is exactly what we see in the question as you are working towards. Now we go back to the integrand. Since x has been given us root 3 times u, right, we're going to find what s cube will be. So s cube is going to be root of 3 times u all exponents 3. Okay, and then that's coming, but 3 is too far. That gives us root of 3 exponent 3, and then times tan u all exponent 3, right? So root of 3 exponent 3 is going to be 3 root 3, and then tan u is going to be tan cube u, right? That's the first part. And in the denominator, we have 3 plus x squared. 3 plus x squared is going to be 3 plus x has been given to be root of 3 tan u, right? So that's has to be squared since it is x squared. Then we get 3 plus 3 tan squared u. Maybe you can factor out 3. Then write 1 plus tan squared u. So that gives us the numerator and denominator after we have changed everything to u, right? And again, remember we are trying to switch from x to u, so this dx must also change, right? That's why we find du in the answer we are working towards. So we write the expression for x is equal to root 3 tan u, and find the x from here. So dx du is equal to root 3, and what is the integral for tan? Sorry, the differential for tan. You can check from the formula page, and then you realize the value is sec squared u, right? Multiply both sides by the u, so that the u would here du here by du. So du here cancels du here, and we realize that dx is equal to root 3 sec squared u. So at this point, we have every information to go back to the integral and then do a substitution, right? We're going to go back to the question. Wherever you find x cube, we replace it by its expression over here. 3 with 3 tan cube u. Do the same thing to the denominator and then dx as well. Then we try simplifying the result and see what we're going to get. So let's do that down here. So now our question becomes, I now becomes, sorry here, we have integral from 1/3 pi, or from 1/6 pi to 1/3 pi of, now that the numerator becomes 3 root 3 tan cube u, as we found at the top over there, all divided by the expression for denominator. I factored out 3, so I'm going to write 3 out here. And then 1 plus tan squared u. Then time dx. dx is now root 3 sec squared u. Or remember, over here, dx is everything here times du. So I needed to bring a du here. So I attach du to this. And that's it. So what we need to do over here to simplify these things, right? I think I can cancel the 3 and 3 over here. And the root 3 and root 3 will multiply to give us 3, right? So we need to write that 3 here. So let me scroll down, and then I is equal to integral from 1/6 pi to 1/3 pi of the numerator becomes 3, and then tan cube u, and then sec squared u times du, all divided by 1 plus tan squared u. Now let's go back to the expression we are trying to work towards. We are trying to work towards this, and then you see only tan cube u over here. It means that something must be done to this fraction, 1 plus tan squared u, and then sec squared u. So you check your formula page, and you find over here that 1 plus tan squared theta, we have u, right? So 1 plus tan squared u is equal to sec squared u. That means that this 1 plus tan squared u can cancel the sec squared u since they are the same. Right? Now our I is equal to the integral of from 1 over 6 pi to 1 over 3 pi of the expression 3 tan squared u and then du as expected of us in the question. Oh, sorry, this is cube, tan cube u. It's good to check your answer, sir. So question number 9b says that hence or otherwise find the exact value of I. Give your answer in the form P plus Q in R, where P, Q, and R are rational. So find the value of I. We've already expressed I in this form. So let me write I first. So we know I initially was given as x cubed over 3 plus x squared dx integral from 1 to 3, and this has been written in the form integral from 1/6 pi to 1/3 pi of tan cube, right, of u du. And the question is saying hence or otherwise, right, find the value of I. So hence find the value of I means that we should continue from where we ended in part A. We should find the value of I using this integral, right? And if you think that is too hard for you to do, and you think this part is easier since it involves only algebra or algebraic expressions or functions, then you go with otherwise, right? So hence means that we continue from here. This is if you have to take hence, and then this is if you have to take otherwise. That means that we can. So hence means continue from where you ended, and otherwise means that you can start afresh and start your integration all from the beginning, right? So I'm going to do both sides. So you pick the one that you think is easier for you. I'm going to go hence. That means I'm going to integrate using the tan expression. So let's go for hence. Right, so you don't need to write it. I'm just writing this for identification purpose. So first we need to know that tan cube u is the same as tan u times tan squared u. And as you saw from the formula page, we also found out that tan squared u is equal to sec squared u minus 1, right? That's exactly what we use to cancel from the part A. So this is the same as tan u times sec squared u minus 1, right? And I think I can also write tan u sec squared u and then minus tan u. You have multiplied tan u by what is in the brackets, right? So to integrate this is also the same as integrating this whole expression. That's what I'm going to do. I'm going to integrate. Let me forget about. Okay, so I'm going to write this. I wanted to discard the limit, but let me still write it so I don't forget at the end. So I have tan u sec squared u minus tan u, right? So we also need to, we're going to integrate term by term. We're going to integrate this part and this part. I mean, the integral for tan u is equal to, so for this one, its integral is negative ln of cos u, right? You can use by substitution by writing tan u as sin u over cos u, and then you replace cos u by x, right? And then you do that integration. Or because for the sake of the law of in this log, you can write this as ln of cos u negative 1, which is 1 over cos u, and that is sec. So So this can be written as ln of sec u, right? So any which way you will still get the answer right. So I'm going to use negative ln of cos u since I can use that on the calculator. Then next is to try and integrate the first part, right? Tan u and sec squared u. Find out from the two expressions what happens when we differentiate one of them. Do we get the other? So you realize that when we differentiate tan u, we get sec squared u, right? So that is a hint that we can use a substitution, u substitution, or one that we call ln substitution, right? So I'm going to replace tan u by a variable. It should be u, but then because we're already using u, I'm going to use an x for that. So let me write over here 1 over 3 pi and then 1 over 6 pi tan u sec squared u minus so over here the integral of tan u is already said to be negative ln of cos u. Oh, and then there is a number I've forgotten to write. There was a 3 here. Sorry, all this while. Okay, so there's a 3 here. It means 3 comes at the end of all these things. Right? Don't need to forget a 3. So it comes down here. 3 here, and there must be a 3 here. Right? Then, so means these two negative signs will tend to a plus. Right? Now what we have doing is to integrate this side, right? And as I said, we're going to use u substitution because I know the differential of tan will give me sec squared u. So I know some things are going to cancel out, but then because you're using u, let's represent tan u by x. Right? That means I'm also supposed to change the limits, right? So that it will be defined for x, but I'm not going to do that because when I finish the integration, I'll bring back the tan x, sorry, the tan u. So I don't need to change the limits any longer. And this is du. So let's find dx. Dx is equal to sec squared u du. That means du is equal to dx over sec squared u. So I'm going to push that back into the integral that we have over here. So we have 3 outside and integral from 1 over 6 pi to 1 over 3 pi. And then tan u is going to be x, and then sec squared u so gets replaced over here, and then du is now dx over sec squared u, right? And sec squared u and sec squared u will be cancelled out. Remember, plus our 3 ln of cos u in absolute, since ln doesn't take negative values. Okay. So what we have integrating is now 3 out, integral from 1 over 6 pi to 1 over 3 pi x dx plus 3 ln of cos u. Remember, ln of cos u doesn't need any integration because that has been done already. Now the left hand side becomes 3 out, and then the integral of x with respect to x is x squared over 2. So it has to be x squared over 2, but I'm going to write the over 2 here since it is a constant. And then I go from pi over 3 and then pi over 6. However, I'm not going to do the substitution over here because I did not change the limits to be defined for x. The limits pi over 3 and pi on 6 are defined for u. So when I get back to the substitution, I'm going to replace the x squared by tan u since I did not change the limit. I'm going to do that straight ahead over here. I'm going to get this out and then replace it by tan u, which is going to be tan squared u Then to the other side, I have 3 out. Then ln of cos u, and then the constant out from pi over 6 to pi over 3 over here. Now next is that we substitute the values over here, the limits. So 3 over 2 out, then I have tan pi over 3 all squared, or tan squared pi over 3 minus tan pi over 6 all squared, close the bracket. And then next is 3 out ln of cos pi over 3 minus ln of cos pi over 6, close brackets. I'm going to point this on calculator and find out the answer. The one in the bracket, in the first bracket, gives me 8. So I have 3 over 2 times 8. Then the expressions in the second bracket gives us negative ln 3 over 2. So we simplify, and then the first term becomes 24 over 2. So the first one gave me 8 over 3 instead of just 8. So it has to be 8 over 3 here. So now it has to be 24 over 6, and that is 4. The next one is going to be minus 3 over 2 then 3, and that is our answer, and that is for the hence parts. Next we look at this from the otherwise parts. So let's go the otherwise way. Otherwise means that we can start everything afresh and then start integrating from the question. So integral from 1 to 3 of x cubed divided by 3 plus x squared dx, right? So it is also an improper fraction, right? Because the degree of the numerator is greater than the degree of the denominator. So we need to do a long division and find the quotient and remainder so that it can be written in a nicer way for us to be able to integrate. We're going to do the long division over here. Put our x squared plus 3 out here, and then x cubed over here. Then we have x here, x cubed plus 3x. You subtract and we get negative 3x, right? X cannot divide this one, right? That means that our expression, the expression over here, x cubed over 3 plus x squared, can be written as the quotient, which is x, and then plus this, or plus the negative 3x over the divisor, which is x squared plus 3. So instead of integrating what we have over here, we're going to integrate what we found out here, right? So let's rewrite the question with a new integrand. So we have integral of from 1 to 3 of x dx minus, going to write the 3 outside, from 1 to 3 of x over x squared plus 3. And I believe you know why the 3 has been written out, because a constant, and we can just write as once you multiply, if bring it inside, it becomes the same expression over here. So let's start integrating. The first one is easier, the easiest, x squared over 2. Then from 1 to 3, right? Then next is 3 here. So let's check something from the formula sheet again. So you have this integrand over here. It says that to integrate a function, right, an expression or a rational function where the numerator, which is f prime of x, is the differential of the denominator. Remember, the denominator is f of x and the numerator is the differential of the denominator. Then the answer is ln of the denominator of f of x. So go back to this and see it over here. What's the differential of the denominator here? Differential of x squared plus 3 is 2x. But that's not the same thing as the numerator. So we need to manipulate the numerator to get 2x. So I'm going to rewrite the integrand 3 1 and then x here over x squared plus 3. Because I want to find, I want to manipulate it so that the numerator becomes the differential of the denominator and the differential of the denominator is 2x. I'm going to write 2 over here with a different color. We're going to write 2 over here so that the differential of the denominator gives you the numerator. However, that changes the question. For me to get back the original question, I need to also divide by 2. So the 2 that is written up here will also be divided down here so that these 2 and these 2 cancel out to give us the original question. Right. Now we have an expression like this. Right. We find out that the numerator is the differential of the denominator. So our answer is going to be ln of the denominator. So let's do that over here. You're going to write okay. So at the left side, at the first term, we can do our substitution and get 3 squared over 2 minus 1 squared over 2. Then next step we have 3 over 2. Now that this everything works perfectly, we need to write ln of x squared plus 3 as our integral. And we don't need to add a c because there are limits. And yes, we can also factor out the 3 over 2 and then 3 1 here. And let's simplify this. We have 9 over 2 minus 1 over 2, or 9 minus 1 over 2. So we have 8 over 2 at the left side. Then minus 3 over 2 bracket, you have ln of 3 squared plus 3, right? That's going to be 9 plus 3, and so that gives us 12. Then minus 1 squared plus 3, that's going to be ln of 4. So we have 4 here. Sorry, let me simplify and write 4. So 4 here minus 3 over 2. Remember ln of a law of logarithm. Ln of a minus ln of b is equal to ln of a over b. So I'm going to write 12 over 4, which is 3. The second one looks simpler and easier, right? So choose wisely whether you want to go hence or otherwise. Now question 10. The variables x and y satisfy the equation given over here where k is a constant. Then we have to show that the differential of the equation given over there is this, right? So two ways we can go about this. You can either multiply through by x plus 2. So what we need to do is to show that when we differentiate this equation, we will give this one, right? So you can decide to multiply through by x plus 2 just to clear the fraction. If you don't want to deal with the quotient rule, I'm not going to do that. I'm going to use the quotient rule. That's the other way of going about it. So let's go to our formula page and check. The quotient rule is this: u over v. Alright. So it means that we are trying to differentiate a fraction, a quotient function. So the numerator becomes your u and the denominator is your v, and this is our formula. Right. We're going to do that over here. We're going to let the numerator be equal to u. So from this, our u is equal to x minus 2, and then our v is equal to x plus 2. I'm sure you want to ask, what about k, right? K is a constant, so you can leave it out. Finish your entire differentiation and then bring back your k, right? If you want to include k in this, then u should be equal to k times x minus 2, which will not help you in any mean. You're still going to get the same thing, so leave out your k, but make sure you don't forget when you finish, We bring back to k since it's a constant. But then if it were a variable, we would have included it in the numerator. So yeah, from the formula, you need to find du dx. So since u is this, du dx is equal to 1, right? And then dv dx is equal to 1, right? So, and then v squared is equal to x plus 2 all squared. There's no need to expand this. So let's differentiate it. So our differential, you go back to the question, you differentiate the left hand side. The differential of y is dy dx. By differential of 2y is done the same way as we do for x squared. Right? So y squared is then the same as we do for x squared. So if you have x squared, its differential is 2x. But for y squared, it becomes 2y and then dy dx as well. Right? That's also the product rule. So differential of the left hand side, the y squared is 2y dy dx. And then the right hand side, bring your k out over here and everything will be done. The rest is, the formula says that v du dx minus u dv dx all over v squared. So we start with v first. V is x plus 2 times du dx, which is 1, minus u, which is x minus 2, times dv dx, which is 1. Then everything divided by v squared, which is x squared, so x plus 2 all squared. Once again, there's no need to expand this as it's going to make the work even more difficult. Now, at this point, we can decide to expand this part, make it negative x plus 2, or maybe you want to also leave it that way and continue your calculation. You still arrive at the right answer, right? So I'm going to divide both sides by 2y because I need to get rid of the 2y at the left hand side since we need to find dy dx. So let's do that. Here by 2y and everything here by 2y as well. So 2y and 2y are out of our expression from the left hand side. Then we have dy dx is equal to k. So I want to write a k out here for a purpose. Then x plus 2. Then the other side we have negative x plus 2 all over 2y times x plus 2 all squared. Remember, we can't expand the left hand side as x plus 2 and then cancel anything or cancel some things over here because of the k here. K is to multiply what is in the bracket first before a multiply. K is to multiply everything at the numerator. That's what it means, right? Now we look at the integral, the differential. We are trying to arrive at something that doesn't have a k. It tells us that we need to find a way to eliminate k from this our differential. So we go back to the question. From the question, yeah. So let me write the question back here. We see y squared is equal to k x minus 2 over x plus 2. So because we need to eliminate k, we need to make k the subject from this equation. Then substitute that into the differential. Okay. So I'm going to make it a subject over here. Into we need to multiply through by x plus 2 so that this and this will cancel, right? So here has to be multiplied by x plus 2. Then when we finish, we divide through by x minus 2, so that this and this will go away. Now we have our k is equal to x plus 2 and then x minus 2 times y squared. So this replaces the k in this differential, and then we'll be closer to our solution. So let's do that over here. So now dy dx is equal to k, which is the whole of this expression, x plus 2 y squared divided by x minus 2 times everything in the brackets, x plus 2 minus x plus 2, all divided by 2y x plus 2 all squared. So let's do some cancellations and then find out what we get to. So x plus 2 here takes out 1 x plus 2, so we have x plus 2 is equivalent to 1 from here. Alright, and then there was a y squared here and there's a 2y, so the 1y here takes out one of the y's here, so we have only 1y over here. Now our new expression becomes y outside, and then in this brackets negative x and positive x are gone, so we have 4, right? So I'm going to multiply the 4 by the y here, so you get 4 times y, all divided by, then at the denominator we have x minus 2 times x plus 2 and then times 2, so we have 2 out, x minus 2 x plus 2 over here. So our dy dx is equal to 4y. Alright, even before the 4, 2 here once and 2 here twice, so the numerator becomes 2y, all divided by, and this is x minus 2 times x plus 4, that is difference of two squares, giving us x squared minus 4. So our differential is 2y over x squared minus 4, and that is exactly what the question expects of us to get. So this is our answer. Now, number 10b, given that k is equal to 5, find the angle between the tangents. So with an S means that there are two tangents to the curve when x equal to 3, and we need to find the angle between them. And the answer must be given in the form a tan inverse of b over c, where a, b, and c are integers. Right? So to find the tan inverse of the angle between the two, then multiplied by an a. So let's go back to the question. We have our y is equal to, I'm going to write the question, y squared is equal to k, then we have x minus 2 x plus 2, and now that we've been given that k is equal to 5 and then x equal to 3, right? I think I should replace the k here by 5 and then the x is by 3, so that you don't need to write plenty. So k by 5, the x is by 3, right? That gives us a simplified number. So we have y squared is equal to 5, this is 1, so 5 times 1 over 5, which is 1, right? Then we find y, we take square root of both sides. Remember, square root of a number has to come with plus or minus, so it means that y is equal to plus or minus 1. So when x is 3, y is plus 1, and when x is 3, y is also minus 1. So I have 2 points. So at x equal to 3, we have 2 points of tangency. One of them is 3, -1, and the other is 3, +1. And we need to find the angle between those two tangents that pass through these 2 points. And we don't need to find any equation of a tangent, right? The tangent between two, or the angle between two tangents is found by this formula. So where theta is the angle, so we have two tangents and then the angle between them is theta, right? Tan theta is given as m1 minus m2 over 1 plus m1 m2. That's the angle between them. And if it's an acute angle, we take the modulus of it, right, to find acute angle. So it means that we need to find where m1 and m2 are the gradients of the um the two tangents, right? So we know that at x equal to 3 there are two tangencies. One is 3 negative 1 and the other one is at 3 positive 1. So we need to find the gradient of the two tangents. One of them is m1, the other is m2. So all we need to do is to substitute the 3 and negative 1 and then 3 and positive 1 into the differential that we found, which was found in part A. So this differential 2y over x squared minus 4. So let's start. For m1, or the first gradient, m1 is equal to 2y, so that's going to be 2 times negative 1 over um, y x minus 4. X is 3, so 3 squared minus 4. That gives us negative 2 over 5, so negative 2 over 5. And then m2 is substituting 3 and 1, so that's going to be 2 times y, which is 1, over m squared, sorry, x squared, which is 3 squared minus 4. So we have 2 over 5 positive, right? So ideally, what we do is that we normally represent the bigger number by m1 and then the smaller number by m2, right? So this would have been our m1 and then this are m2. And then because we want to get positive number, then because of the modulo sign, it changes nothing. We still get the positive even if we interchange those two numbers. So now the angle is um, tan theta is equal to the modulus of 2 over 5 plus 2 over 5. So I start with the first one, 2 over 5, then minus 2 over 5, all divided by 1 plus 2 over 5 times negative 2 over 5. So at the numerator, and then I'm pointing everything straightforward, and then we get 20 over 21, right? Now since we have to leave our answer in the form A tan inverse of B over C, we need to take tan inverse of both. So we have tan theta is equal to 20 over 21, tan inverse of both sides, and then you have theta is equal to tan inverse over 20 over 21, and this is in this form. Then A is equal to 1, B is equal to 20, and C is equal to 21, and that is a answer to question 10b. Question number 11. The points A and B have position vectors given over here, and then we have to show that the perpendicular distance from A to the line through O and B is 1/3 root of 65. So there's a step-by-step approach to this, and there's also a formula to use. For the sake of understanding, I'm going to use the step-by-step approach, and I won't use the formula approach since you don't have that formula in the formula sheet, right? So let me do a simple sketch here. So O here, and then A is relative to the origin, and let's say our B is somewhere here. Okay, let me use a straight line. Let's say B is somewhere here. Okay, then A is somewhere over here, and there's the origin. We are to show that the perpendicular distance from A to the line through O and B. So there's a line that goes through A, O, and B. Let's call that line R, right? So a line going through O and B is called R. You need to find the distance, the perpendicular distance, so a perpendicular line from A to B to this line, right? Meeting is 90 degrees. And we need to let the foot of the perpendicular be called P. Our job is to find the line AP, right? The distance AP, right? So yeah, we are through this calculation, we are going to let P be the foot of the perpendicular. So let me write that here. Let P be the foot of the perpendicular. So of the perpendicular from A to the line through O and B, right? So wherever we see P, this will become our interpretation. You need to find the line through O and B, right? So remember that line is going to be R is equal to, so it has to be R is equal to the initial point, right, where the line is starting from, and then so the initial point plus, we start from O, which is origin, plus um lambda times OB, right? So R is going to be the initial point O plus lambda OB, but O is 0, 0, 0, so that can be discarded. So that's R is equal to lambda times OB, and OB is 4i plus 2j plus 4k, right? So that's the equation of the line R. And now P lies on this same line, right? So P still also has the same value as the equation of the line, just that P just needs the value of lambda to determine the actual value of P. So I'm going to write OP and write the same equation for the line for P, since P lies on the line. It's just more like having a Cartesian equation. Y is equal to 2x plus, let's say, 3, right? And then there was a point P on this line. I don't know what P is, but then if you give me the value of x, right, then I'll be able to find y and I'll tell you what P is. So I can replace this whole equation by P, and then I'll be looking for what value of x P is, or what value of y P has, so that I'll find the corresponding value for x or y. Then I'll find the value of P. That's why I'm replacing the whole of P by this. I'm going to parameterize this. I'm going to write OP is equal to um, lambda, and then write as a column vector 4, 2, and 4. So column vector instead of parameterization, right? So this is for OP, right? Or you can write it as 4 lambda, 2 lambda, and then 4 lambda again. Mind you, since you are writing it this way, there's no need to bring ij and k. It is wrong to bring ij and k. Once I write as a linear form like this, or as a unit form, then we need to add a ij and k. But once it comes in a column form, it doesn't require any ij and k. Now that we have OP, you can find AP because you know OA, right? OA is 2, 2, and negative 1, and OP is 2, 4, 2, and 4 lambda. So let's find AP. The vector AP is equal to OP, the end vector minus the initial vector. So that's going to be 4 lambda minus 2. Remember, A is 2, 2, 1. So you have 2 lambda minus 2, and then 4 lambda. A has negative 1 as the last value, so it becomes 4 lambda minus minus 1, becoming plus 1. So that's AP. Now what we need to now do is to find the value of lambda, so that AP will be numbers, right? And once they become, everything becomes a number, then we can find the distance or the modulus, right? So how do we find the value of lambda? What other information do we have? The idea of perpendicular brings to mind that there should be a scalar product equated to 0, right? We know that the line AP, right, vector AP meets the line R as 90 degrees, right? So we need to find the dot product of AP and then R and then equate to 0 since they are perpendicular. You're going to find AP dot R, but you're not going to use the entire of R. Has this equation. You're going to use a direction vector, right? I'm going to use dr to show direction vector of R should be equal to 0, right? So the direction vector of R is basically the part that is multiplied by lambda. Fortunately for us, R doesn't have any other parts apart from this part. So if R had something, let's say plus some 2i, then something blah 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 over here, then we are still going to use the part that is attached to lambda, right? We are not going to use the whole of R. So let's say the direction vector is 4 to 4, even without the I and then the lambda, right? So AP is 4 lambda minus 2, 2 lambda minus 2, and then 4 lambda minus plus 1. Then the dot product of this and then the direction vector of R, which is 4, 2, 4, should be equal to 0. So you find a dot product and equate it to 0. So it's going to be 4 times 4 lambda minus 2 plus 2 times 2 lambda minus 2 plus 4 times 4 lambda plus 1. And then it should be equal to 0. So what do we have? We have, I think we can divide through by 2. Let's divide through by 2 so that it becomes reduced. You have 2, 4 lambda minus 2 plus 2 lambda plus minus 2. So 2 lambda minus 2. Then plus 2 out 4 lambda plus 1 is equal to 0. So let's expand. 8 lambda minus 4 minus 2 lambda minus 2 plus 8 lambda plus 2 is equal to 0. So we have 16. Sorry, there is a plus here that has been changed to plus plus. So 16 plus 2 is 18 lambda. Then for the constants, you have negative 4 because negative 2 and positive 2 are out. So you have negative 4 is equal to 0. So you get equal to 0. And then lambda is equal to 4 over 18, which is 2 over 9. Right, so that gives us the value of lambda, and then it makes it simpler for us to find AP. AP is, so we just need to substitute the value of lambda, and then we get the value of the vector for AP in numbers. So AP is equal to, the vector AP is equal to 4 lambda, so 4, 2 over 9, then minus 2. We also have 2 lambda, 2 over 9 minus 2 again. Then we have lastly 4 lambda, which is 2 over 9, and then plus 1. Plus 1 is going up. Plus 1 over here. So we have over here 8 over 9 minus 2, and for the first number, we get negative 10 over 9. The next one, 4 over 9 minus 2 will be negative 14 over 9. And the last one, we have 8 over 9 plus 1 has to be 17 over 9. Right? And everything is over 9, so you can just write 1 over 9 out and write the rest of the numbers. Negative 10, negative 14, and then positive 17. And you can find the distance AP. That's what we've been finding all this while, right? From the diagram that's over here, what we want to find is the line, the distance of the line AP, because that is a perpendicular distance from A to the line through O and B. Okay. So, and you have to show that the answer is 1/3 root of 65. So you find the distance. So the distance AP is equal to root of, because um the 1/9 is a scalar, you need not to write it inside the root. If you want to, you can still write it. So you can write it down outside here, then just square the ones in the vector. So 10 squared plus 14 squared plus 17 squared. I hope you have no problem seeing that there are no negatives attached, because negative squared and positive squared give the same result. So we have 1/9, and everything in the bracket gives 3 with 65. Right, so AP is equal to 3, 6, 3 out of 9. So you have 1/3 root of 65 units, as the question requires us to have. That's our solution. And now the very last question, 11b. The point C has position vector OC equal to 3i plus pj plus qk, where p and q are constants, given that OC is perpendicular to OB. So, and then angle AOC is equal to angle COB. Find the values of P and Q. So here, OC is perpendicular to AB, means that the dot product of OC and AB must be 0. So OC dot AB should be equal to 0. And that's the information we need to find one of these constants, which is going to be Q. So let me write OB and OA here. OA and OB were given. So OB was given as 4i plus 2j plus 4k from the previous question. And then OA was given us 2i plus 2j minus k. Right. So from here we can easily find our OC has been given, so we need to find our AB. Right. So AB is the end vector minus the initial vector. So OB minus OA, and that is so you are subtracting the A from B. So 4i minus 2i is equal to 2i. Then 2j minus 2j is 0. Then we have, so let me add plus 0j. Then 4k minus minus k is going to be plus 5k. And that is our vector for vector AB. Now the next thing we need to do is to find the dot products. Right. So OC dot AB is equal to, just multiply the corresponding component. So 2 times 3. So 2 times 3. And then P times 0. Then lastly Q times 5. So 5Q. And it must be equal to 0. So we have here 6 plus 5Q is equal to 0. You make Q the subject and Q is equal to negative 6 over 5. So the value of Q has been found to be negative 6 over 5. Now let's move on to the other information to find the value of P as well. The second condition, from the second condition, angle AOC, right, is equal to angle COB. So let's do this. Let's angle AOC be theta. AOC be theta. And then angle COB, let's say be alpha, right? And how do we even find angles? For angle AOC, AOC is between angle AO and then OC, right? Remember, we have A, O, and C. We want to find angle AOC, right? So between AO and then CO. So either both arrows are pointing to the same direction or they are pointing away from a common point. So if I use AO, then I should use CO. But if I use OA, then I must use OC. So either they are going away from a common point or they are going towards a common point, right? So I'm going to use OA and then OC. So how do you find angle AOC from vector dot product or scalar products rather? We have angle or vector OA dot vector OC should be equal to the magnitude of OA times the magnitude of OC and then cos theta. That means cos theta is going to be this whole thing over OA, the magnitude of OC. Likewise, you do the same thing for alpha, right? And then you get that cos alpha is equal to OC dot OB divided by the magnitude of OC and then times magnitude of OB, right? And because the angles are the same, then cos of theta should be equal to cos of alpha, right? So cos theta should be equal to cos alpha since alpha and theta are already the same. Right? Then it means that OA OC, sorry, OA dot OC rather. So I go OA dot OC divided by magnitude of OA, magnitude of OC should be equal to OC dot OB divided by magnitude of OC times magnitude of OB. And from here, you can do a simple cancellation over here because there was an OC at the bottom of both expressions, right? You can multiply through by OC so that OC and OC will be cancelled out. So what we have now is OA dot OC over OA magnitude is equal to OC dot OB divided by OB magnitude. Remember, these ones are vectors, right? So this is what we need to make sure the angles are the same. So we need to, we already have OA, OC, and OC. We also have OB. We just need to find their dot products and then their magnitude, and we are good to go. So we have over here our A has been given 2, 2 and negative 1, and then C was given up here as 3P and Q, right? So I'm going to find OA dot OC. Let me use a black color. So OA dot OC will now be equal to 3 times 2, then plus 2 times P, and then plus Q times 1. But then Q has been found to be, so 3 Q times negative 1, so that's going to be negative Q. But Q has been found to be negative 6 over 5, so we're going to write 6 over 5 straight ahead over here. Okay. and then this simplifies to, so 6 over 5 is the same as 1.2, so I add it to 6 over here and I get 7.2. So I'm going to write 7.2 plus 2p. Of course, you can work in fractions, but I don't want to be writing something over something. I mean, wasting my space, right? Now, next to find OC dot OB as we require. Let's go back and check OC and OB. OC is 3p Q, and then OB is 424, right? So you multiply them, you find a dot product. So 3 and 4, 3 times 4, then plus 2 times p again, and then lastly plus 4 times q. But you found q to be negative 6 over 5, which is the same as negative 1.2. Then finally we have again we have 7.2, right? Because this is 12 and this is 2 times the previous one, so we have 7.2 plus 2p. So we found the dot products, and next we need to find the magnitude of A and then the magnitude of B as well. So the magnitude of A, or vector OA, remember A is 2, 2 and negative 1, so it's going to be root of 2 squared plus 2 squared plus 1 squared, and that gives us 8 plus 1 is 9, so that gives us 3. Then we do same thing for OB. Magnitude of OB, remember B is also 424, so it becomes 4 squared plus 2 squared plus 4 squared. So we have 32 plus 4, 36, so the magnitude is 6. Right, so you have it all to do substitution into this equation, and then we're able to find the value of P since Q has been found already. So let's do our substitution. So first we have 7.2 plus 2p all over magnitude of A, that is 3, should be equal to the same thing, 7.2 plus 2p divided by magnitude of Q of B, which is 6. Now we can solve this, right? We can multiply through by 3 so that this will be cancelled and this will become 2, right? Then we cross multiply. So 2 times 7.2 plus 2p should be equal to 7.2 plus 2p. So we have 14.4 here plus 4p is equal to 7.2 plus 2p. Now 4p minus 2p, you're going to have 2p, and then 7.2 minus 14.4 is another 7.2 but negative. Right, now we divide through by 2, and then we find p to be negative 18 over 5. So yeah, p is equal to negative 18 over 5, and then q as found earlier is equal to negative 6 over 5, and these are answers. So that's the end of the paper. Make sure you subscribe and then hit the notification button so that you'll be updated on any new developments. Thank you for watching, and all the best in your preparation towards your examination.